So, and this is very directly analogous to the Higgs boson in the standard model of particle physics. We have examples of this that we know work in particle physics itself. So this expansion, this vacuum expansion, has a neat property in that the expansion of the universe, instead of slowing down, right? If it's full of dark matter or something, the self-gravitation of all the galaxies, you would expect it to gradually slow the expansion down. When the universe is full of vacuum energy, the expansion of the universe actually speeds up, it accelerates. So now, instead of seeing more and more of the universe as time goes along inside our observable universe, during inflation, your observable universe stays approximately constant, but the universe expands exponentially quickly. So somebody who starts out inside your observable universe very rapidly gets stretched outside of it. This explains the homogeneity, right? So these guys can start out, this little patch of the universe starts out being pretty much homogeneous because everything can talk to everything else. But then the expansion is so rapid that that little homogeneous patch gets stretched out way bigger than the observable universe and stretches out and explains why the initial condition for the Big Bang is homogeneous and isotropic and flat and all of these things, right? So inflation also explains the flatness of the universe, because if I have a little patch, for example, on a sphere, and if I'm on a very small planet, I could actually see the curvature going out to my horizon. But if I blow that planet up really huge, my local area looks perfectly flat. My observable universe my horizon looks perfectly flat, just like on the Earth, right? It looks flat to us all the way out to the horizon. So the way inflation explains the flatness of the universe is if there's a little bit of curvature initially, it stretches that out so big that you can't see it within your observable universe. And in particular, you get something for free when you add quantum mechanics in here. The vacuum isn't actually empty, it's full of little virtual particles. Quantum mechanics tells us that the vacuum is really a very busy place. And these virtual particles, or these quantum fluctuations, also get stretched with the expansion. So they start out smaller than the observable universe and they get stretched bigger than the observable universe. This is like, you maybe heard about Hawking radiation from black holes, this idea that you have a virtual particle pair that's produced near the horizon of a black hole. One of them falls in and the other one escapes. How many people have heard of that? All right, this is exactly the same process as Hawking radiation, except here you have a virtual particle pair that pops out of the vacuum, and the universe is expanding so fast that they get stretched outside each other's observable universes before they can recombine. And this is the process which creates those initial fluctuations in the universe, those fluctuations we see in the cosmic microwave background. And it's predictive. It predicts a very particular statistical form for what those perturbations in the CMB ought to look like. So you can give me a particle physics theory of at very high energy. I can turn the crank and I can calculate via this process what the fluctuations in the cosmic microwave background we observe ought to look like. And it matches them exactly. So this is now this process of these quantum fluctuations getting stretched out to these huge, long super horizon scales allows us to actually have observational access to this period, because this is when the fluctuations that collapse to form galaxies were actually formed. They were formed by quantum mechanics during inflation. And it's a predictive theory that we can actually go out and check in the cosmic microwave background, and it's been successful, right? So this pattern of primordial perturbations actually is predicted by the inflationary theories. And in fact, it was predicted before they were observed. And these fluctuations actually match the predictions of inflation to extremely high precision. So this is, now we're not doing philosophy, we're doing real science. We can actually test models of inflation by using the cosmic microwave background, the distribution of galaxies, and so on, because it is quantum mechanics during inflation that set these initial conditions for all the structure in the universe to form. So quantum fluctuations, the same fluctuations that sort of structure in the current universe. Here's the thing, if we're looking at this thing rolling down this hill, this thing is going to be bouncing around a little bit because of quantum mechanics, right? Because of the Heisenberg uncertainty principle. And quantum fluctuations are as likely to push this thing up the hill as down the hill. So when these fluctuations are big enough, in fact, this thing keeps getting pushed back up to the top of the hill again. So as it falls off, sometimes it will fall off and go all the way to the bottom, but sometimes quantum fluctuations will push it back up to the top again. So in this picture, because of quantum mechanics, if those fluctuations are big enough, there will always be regions of the universe where inflation continues to go on forever. Those regions are getting bigger exponentially quickly. So you will have inflation ending locally, but in a bulk in between them, it will still be going on because the field will be quantum fluctuating back up. This is called eternal self-reproduction or eternal inflation. And so the picture of the universe that you get out of this when you add this, when you take quantum mechanics into account self-consistently, is not that this process of vacuum decay happens once and then once and done. It happens in one region, but then there's going to be other regions outside of it that are still inflating. And then there are going to be other regions that decay into a different vacuum, and there are going to be other regions that decay and so on. And so the picture you end up with of the universe is a little bit like a glass of beer, right? So in this metaphor, right, the beer itself is the inflationary part where the field is in the symmetric state. In fact, bubble formation in beer is a phase transition of exactly this kind of type. It's a form of symmetry breaking, right? And so when the beer is the unbroken state, when the field is up here and the universe is expanding exponentially quickly, but then it decays down into the broken state only locally and forms a little bubble like that, and that bubble wall expands out faster than it expands outward at the speed of light. But these bubbles are being pulled apart from each other faster than the speed of light, so they never run into each other, they never percolate. And so you just keep producing more and more and more bubbles, an infinite number of these bubbles. And each of these bubbles contains within it an infinite universe like our own. And the way this works is if you draw a diagram of space and time, right, this bubble that is expanding outward at the speed of light, if I plot time on the vertical and space on the horizontal in the right unit, so that time is in seconds and space is in light seconds, or time is in years and space is in light years, this expanding bubble wall makes a 45-degree angle or sweeps out a cone in here, right? So I can do this again. So this bubble is expanding outward in space, but in time then the edge of that bubble actually sweeps out a cone in space-time. And in relativity, since I can borrow space and turn it into time, or borrow time and turn it into space, I can take some of that infinite future time and turn it into an infinite space, and I can nestle an infinite universe inside that finite bubble. So to someone outside the bubble, it looks like a sphere that is expanding outward at the speed of light. To someone inside the bubble, it's an infinite universe. And the bubble wall is everywhere in your past. It's not a boundary in space, it's a boundary in time. This is now what we replace the initial singularity with, is that end of inflation when the universe goes from a symmetric state into an asymmetric state. It creates an infinite universe inside this finite bubble. Kind of like some sort of magic thing from Harry Potter or something, right? And so then what we do is time goes this way and space goes that way, and we have a nice infinite universe that comes into being all at once as a result of this bubble nucleation in our beer glass universe. And this is happening continuously and goes forward in time infinitely. This happens an infinite number of times, and so the inflation never ends. It's just continuously producing new universes like our own. They're all causally disconnected. You can never travel from one bubble to another because you'd have to go back into the past before the Big Bang to get out of your bubble. And so in this picture, then, our universe is just one of many and many, many. And this is reminiscent of the Renaissance philosopher Giordano Bruno, who wrote, "God is infinite, so his universe must be too. He's glorified not in one, but in countless suns, not a single earth, a single world, but in 1,000,000. I say in an infinity of worlds." Giordano Bruno wrote in Cause, Principle, and Unity that to know the universe is to know nothing of the being or the substance of the first principle, because it is like knowing the accident of accidents. He was grappling with the same problem as modern cosmologists with a remarkably prescient sensibility. Bruno's resolution of the paradox of Aristotle's paradox of the first mover was to adopt a radical expansion of the Copernican principle that the Earth was but one of an infinity of worlds. So he was more Copernican than even Copernicus was. And this Copernican idea provided Bruno with an organizing principle through which to comprehend an unbounded and ultimately unknowable cosmos. And in inflation, we see Bruno's infinity of worlds extended to an infinity of universes, of which ours is but one. And of course, this is the source of the title of my book. And I thank you very much for your patience.